Okay, so let's start my talk. At first, I would like to express my sincere gratitude to EPSRC and JST for providing this fantastic opportunity. So I'm particularly grateful to Ms. Kaneko for her tremendous support. So having spent 3 years as a postdoc in the UK, so it's a great honor for me to present at this event. So, well, I'm a bit nervous, but let's begin. So let me start with a brief introduction about myself. So I was born in 1981. So this is the same year. So Richard Feynman delivered his famous lecture on quantum computing. So then in 2005, I started my final year's project. So in computer chemistry and quantum chemistry. So this was also the first year of the first paper combining quantum computing and quantum chemistry was published. So my lab is somehow related to quantum computing. So, and then I did a postdoc in Bristol, 2011 to 2014. So Bristol is a fantastic city. I enjoyed the postdoc life there. And so there, I supported by the Molecular Research Fellowship and the Canon Research Fellowship. During this time, my advisor, so Dr. David Tu, now he's at Oxford, was collaborating with Jeremy O'Brien, who is now the CEO of PsyQuantum. So I had an opportunity to attend a lecture of O'Brien in Bristol, where the first variation of quantum eigensolver papers. Its result was shown, focusing quantum simulation on molecules like helium-8+. But at that time, I was not keen on quantum computing because the error was so huge. But later, in 2018, although myself not directly involved, I followed the paper published by these two guys on Nature, so which sparked my interest in quantum computing. And so that same year, so I began collaborating with a startup company of quantum computing, so called Clinisys. So I started the research on quantum computing from 2018, and 2019, I was invited by Professor Keisuke Fujii and Makoto Negoro. They are the co-founder of Clinisys to join Osaka University. So since then, I have been fully dedicated to research in quantum computing. So let me introduce our center, the Center for Quantum Information and Quantum Biology. The QIQB is located on the Toyonaga campus of Osaka University, which is the north of Osaka. So it's very close to airport and not so far from the central part of Osaka. So Osaka is known as the second largest city after Tokyo, and close to Kyoto and Nara, so they are famous for sightseeing spots. So in my opinion, though, the location is great. And QIQB is a young center. So it was established in 2018. So I joined the center in 2019, but at that time, QIQB is almost virtual research centers. There's no official room or buildings at all. But now QIQB is one of the Osaka University's flagship centers, and it is strategically important to the universities. So now it is one of the largest center of quantum information science in Japan. So there are currently more than 70 researchers at QIQB. And roughly half of these total researchers, so including me, work exclusively for QIQB rather than in other roles. And this number is continues to grow. And QIQB has 6 major research domains as outlined on this slide. So quantum sensing, quantum computing, and quantum information devices, and quantum communication and security, quantum interdisciplinary quantum science area, and quantum biology. So QIQB covers many quantum technology research fields. Also, QIQB hosts the Quantum Software Research Hub in Japan. This project develops the full stack quantum software required for quantum computer. So from low layer software such as middleware for manipulating quantum processing unit to application layer software. So we are also operating the third made in Japan superconducting qubit in Osaka universities as a test bed for this purpose. Plus, we are developing ion trap machines now. So in QSRH, this research hub, I'm in charge of developing quantum software for chemistry and condensed matter physics. So as you've seen that our center covers a wide spectrum of quantum-related research areas. So our QB internal structures shown on the left represent how these fields are interconnected with QIQB, within QIQB. So each area benefits from close collaboration with the others, creating a synergetic research environment. And through our Aspire project, funded by JST, we are now expanding our international network as illustrated on the right-hand side. So our aim is to establish QIQB as an important research hub in quantum technologies by extending our international network through international collaborations. So previous slides, I mentioned that our center established quite recently and growing. And unfortunately, our international activities were limited by COVID-19 from 2020 to 2022, which coincide with the growing phase of our institute. But now, luckily, so we have the Aspire research project and its grant, and it allows us accelerate our visions. So we are very grateful to JST. And this is the goal of, future goal of our Aspire project. So our ultimate goal of the Aspire project is to enable seamless quantum processes. So from quantum sensing of molecules to quantum computing, while keeping entanglement for the processes. So we are aware, of course, we are aware that this is not something achievable in the next 5 or 10 years. At this stage, it might still sound like sci-fi stuff. However, we want to turn this sci-fi into reality within the next 20 years or so. So if achieved this goal, this vision will rely on extensive international research networks, it should be. So uniting experts from quantum biology, sensing, quantum devices, and quantum communication, and quantum computing, and so on. So together, so they will tackle the challenge and create the transformative future. So I think that the networking between and covering these wide range areas are important for futures. So the objective of our Aspire project is to plant the seed of such a network today, and by connecting researchers across these fields, so we hope to raise the groundwork for this ambitious future. So to achieve our ambitious goal, we have divided our research into 3 main teams. So the first team working on quantum sensing and quantum biology teams with universities. And the second team works on developing quantum devices and quantum communication technologies. So these are designed to eventually relay data from quantum sensing to quantum computer. For this, we are collaborating with IMEC in Belgium and the New York University in the United States. So finally, so the third team focuses on quantum computing. So this research is conducted in collaboration with the University of Oxford and QQB. So since today's event is the UK-Japan Quantum Technology Networking Fair, so remaining of this presentation will focus on our quantum computing collaboration with Oxford. So then I would like to explain how our collaboration with Oxford began. So it began in 2023. So as we mentioned that until 2022, so we had a problem of COVID-19. So we started kind of collaborative work from 2023. So in 2023, so several key steps were taken to strengthen the collaboration between QIQB and Oxford. And for example, PhD student from Oxford or researcher from Oxford visited QIQB for a while to work on quantum computing. And a copy of our Aspire project, Koichi Miyashi spent time at Professor David Lucas' ion trap laboratory for nearly 1 year. And also researchers from QIQB and Oxford held a workshop at Oxford just 1 year ago. Okay, and then, so Koichi stayed Oxford at the time and he asked David Lucas was the possibility of collaboration and how to let's apply to Aspires. But he suggested that, he introduced us to Dominic O'Brien because in Oxford, there is an institute called Oxford Quantum Institute, which covers more than 60 groups involved in quantum sciences. So he suggested that rather than focusing on a single lab, linking up with OQI, as it proposed is to connect different quantum research areas, so including not only the ion traps, but also quantum biologies and so on. So David Lucas introduced us Dominic O'Brien, who is acting director of OQI at that moment. And with his support, we received a letter of intent to apply for Aspire funding. And luckily, we were successful for that funding. So this project with Oxford is not limited to a single research lab, but seeks to foster wide collaboration between OQI and QIQB across various quantum disciplinaries. So this slide highlights a significant achievement from the collaboration between the University of Oxford and Osaka University. So the time is limited, so let me briefly explain the highlights. So this algorithm allows us is a novel algorithm for efficient quantum simulations, and which uses a random circuit with only 2 rotation angles. So it means a robust against noises. And also the good point is that no plot errors, no algorithmic errors. And it also shows that better performance than the standard trotter approximations. So I think this is a great result, what we get so far. And also that, I would like to share the QIQB networking experience at Oxford. Yes. Yeah. So this research is conducted by the Kiyomi Chuse, who is funded by this Aspire project with Dr. Barnett Koza at Oxford. And Chuse and Dr. Miyanashi enjoyed the life in Oxford. And for example, Dr. Chuse spent 3 months in the UK, and he participated in the quantum emulation 2024 in London. And this event helped him connect with key players in the UK quantum community, not only academics, but also industrial partners. And secondly, both Koichi, Dr. Miyanishi, and Chuse regularly join the this quantum notch event, which regularly held in Oxford every Friday. So this Friday meeting brings together research across the quantum field for experimental theoretical work covering both hardware and software development. So looking ahead, we plan to continue sending QIQ members to Oxford. So I believe that events like Quantum Notch will be very valuable platform for developing new collaboration with Oxford. Okay, before concluding, well, let me share some exciting news. So the coming year 2025 is designing as the International Year of Quantum Science and Technologies. To celebrate this, we are organizing a large-scale international conference on quantum technology called Quantum Innovation 2025, which is also partly supported by this Aspire project. So this event will take place in Osaka in this summer at a venue community located in the center of Osaka. So coincide with this, so there is the Expo 2025 in Osaka will be also held. So I think this is a good opportunity, fantastic opportunity to visit Osaka and QIQB. Thank you for your attention, and I hope to see many of you there. Many thanks.
Thank you. For the sake of time, can I invite Michael Cuthbert to present next? If there's time, we can try and have questions afterwards.
Okay, thanks, Adam. Hopefully everybody can see my slides okay? Yeah. Very good. Well, thanks for the invitation to speak this morning, and lovely to join everybody. I was really intrigued with some of the parallels from Mizukami-san's personal journey to my own, in that I also did a postdoc at University of Bristol about 15 years prior to Mizukami-san. And then I lived in Tokyo for 2 years when I worked with Oxford Instruments, and so got to know many of the Japanese research community, and certainly the prestigious universities that that use some of the cryogenic equipment that we were involved with at the time. So lovely to be able to join you this morning. What I wanted to do was to share a little bit of the UK Quantum Technologies Programme, and then say something a little more about the National Quantum Computing Centre. And I think most of you will be familiar with the UK has had a Quantum Technologies Programme running for a decade now, so since 2014, when we established the National Quantum Technologies Programme. And over that period of time, there's really been very significant investment from both public and private finance into the UK programme. So it's in round numbers about $1.4 billion over 10 years that has been invested into that national programme. And you can see from some of the numbers on the screen there, not quite, but almost half has been invested into research, into quantum technologies and quantum science. And certainly in the UK, there have been many world-leading first results metrics across the whole of quantum technologies. But a very significant amount of that investment has also been in innovation, in really trying to translate quantum science out of the lab into an emerging industry sector to really drive societal benefit and economic growth. So about a quarter of that funding has supported collaborative R&D projects, typically industry-led, but with partnering with academic institutes and academic research communities. And that's driven significant private investment into quantum technologies and quantum startup companies. So the UK has almost 50 startup companies employing now over 1,300 people, in that emerging industry, of which about half are quantum computing companies, but there are still a significant number in networking, in quantum imaging, and in quantum sensing, right across the whole technology sector. And in combination, they have raised venture capital investment of about $1.1 billion in terms of that kind of startup capital to grow that industry. The remaining of the program funding has been split between developing infrastructure and our skills agenda. And on the infrastructure, and I'll talk a little more about the National Quantum Computing Centre in a moment, but thinking about the capabilities through their national lab structure, the National Physical Laboratory, working on standards and metrology, and the development of the National Quantum Computing Centre. So like QIQB, we are quite a young organization. We were established in 2020 and have been working to build up our infrastructure over the last 4 years or so. And then also how we've developed a research hub structure, and then also thinking about how we might employ quantum science and quantum technologies to drive fundamental physics understanding. So where can we use enhanced sensing? Where can we use quantum timing to explore topics like a study of dark matter, gravitational waves, and the like, and where we are beginning to develop capability at the Bowlby Underground Laboratory, which is a salt mine in the north of England, that we actually have some quantum technologies at 1.1 kilometers underground. And then the final piece is really about developing skills, building an ecosystem, and ensuring that we have a pipeline of really talented, bright people that we can actually move into this emerging industry as it develops. So we've run a number of doctoral training centres over the last 10 years, and have just recently announced 5 more, focused on training PhDs. But then we also have other apprenticeship and technician programs, as well as an increasing number of programs from the National Quantum Computing Centre, where we're thinking about how do we provide ongoing career development and continuous professional development for people who perhaps have already developed skills in systems engineering, in telecoms, in computing science, and in adjacent areas, that we can bring them into quantum technologies such that they don't need to go back to the beginning and start with a PhD in physics, or in quantum physics, but actually utilize all the skills that have developed over time. I think it is fair to say that the first decade of the UK's quantum program has really been about that translating science from the lab into industry. So we've had 4 quantum hubs that are focused on academic research, bringing a whole network of university colleagues together, and also working with industry. And then in the kind of second half of that decade of investment, developing industry-led collaborative R&D and feasibility studies, examining topics across sensing, computing, imaging, and issues of position, navigation, and timing in particular. And that's really been a huge focus of effort over the last 5 years in particular. And I should say this is not just funded directly through UKRI and the various research councils, but working across different government departments with the Ministry of Defence, with the Department of Science, Innovation and Technology, GCHQ through the Foreign Office, and also with National Physical Laboratory. So there's a whole number of partners across government ensuring that this becomes a very coordinated program. And I just wanted to highlight a few examples here where we've seen some really fantastic examples of university colleagues working together with either startups or industry partners, exploring new applications, so really trying to drive value from quantum technologies. And even if it's still at that very early stage, how do we push quantum technologies forward? So, for example, a startup company in Nottingham, Circa Magnetics, working with the University of Nottingham, looking at how you can actually use quantum sensors for imaging, health imaging for a wearable brain scanner. Innovative and the University of York, looking at how you can actually put quantum technologies on satellites and get that into space for future communications. As we drive towards a net zero energy environment and think about how we measure emissions and greenhouse gases, a startup from the University of Bristol, QLM, have been working with the University of Bristol in monitoring emissions from pipelines at ever higher degrees, looking at ever smaller molecules. BT, Toshiba, and across the national program have established the first commercial trial for a secure communications network testbed across the City of London, and starting to involve real use cases with real partners from the financial services community. Thinking about how we integrate photonic systems through Orca Computing in the University of Southampton is another example of not necessarily just the full stack quantum computing, but actually what are all the necessary interconnects that we will need for a data center of the future. And then the last example here in seeing the invisible underground. So there's an incredible statistic that apparently, well, anybody who's visited London will have seen this in action, but 50% of the holes that are dug in the road in London are in the wrong place because the underground infrastructure isn't well mapped out when a utilities company go to investigate what's underground. And so RSK have been working with the University of Birmingham to develop gravity gradient sensors such that with ever increasing precision, you can actually map out the infrastructure that is hidden under the ground so that you actually have a much more accurate a map of that hidden infrastructure. So just some examples of where we're trying to leverage quantum technologies and those applications. For the next stage, we've got 5 new research hubs in computing, headquartered at the University of Oxford, in networking, Heriot-Watt University, biomedical sensing at the University College London and University of Cambridge, position, navigation and timing at the University of Glasgow, and then sensing, imaging and timing at the University of Birmingham. And that transition from our 4 previous hubs to refreshing those to these 5 new hubs has only just happened. So the hubs themselves are actually just starting to gather momentum as they get themselves established. And in parallel, we've been working with government to define 5 quantum missions across these same areas where we can really drive that societal benefit and in particular see where industry can start to take these science breakthroughs and really drive them for value and into applications. So the final thing I wanted to share with you was just a kind of quick picture of the National Quantum Computing Centre. So recognizing that quantum computing has a much longer roadmap to large-scale fault-tolerant computational capabilities than some of the other technologies. The UK government recognised in 2018 there was a need for a new national lab solely focused on quantum computing and scaling quantum computing technologies. I think what we've seen over the 5-year period is actually we've been increasingly focused not just on thinking about how we scale technology, but how do we scale the user community and how do we drive user adoption in quantum computing and make sure that is seamlessly integrated into high performance compute workflows such that user adoption is really driven into industry and that we create that user demand for quantum computing as the technology develops. So we are a collaborative program within UKRI across 2 of the research councils, so EPSRC and our colleagues at STFC, the Science and Technology Facilities Council, with an initial 5-year investment, of which about 3/4 of that investment was our new facility and the equipment to actually get the facility up and running. And we've had some further program acceleration during that lifetime. And we've been focused on technology, infrastructure, driving applications, and we formed a very strong partnership with the University of Edinburgh for the Quantum Software Lab to complement the, and again, very similar to QIQB, we also have about 70 researchers across hardware, software, and applications. And at the University of Edinburgh, where the Quantum Software Lab, they have around 50 researchers working, PhD, postdoc, and principal investigators working on all aspects of quantum software benchmarking and verification, and then also thinking about skills. A major initiative we've been running recently is developing a suite of commercial test beds within the National Quantum Computing Centre. So we have supported 7 commercial platforms across most, not all, but most of the different modalities of hardware, across photonic systems, cold atom, tweezer arrays, trapped ions, silicon quantum dots, and superconducting platforms. And this is going to run as we're coming towards the end of the 15-month deployment period to actually bring all of these platforms together under one roof, and then to drive a benchmarking verification exercise over the next 24 months to really examine what are the error rates, what are the noise limitations on these different platforms, do we understand how error correction can be applied, and indeed, can we start to identify the type of algorithms that are best suited for the different modalities rather than assume that one technology will be the winner, which is often what we hear from industry where they've already made their choice about which technology is their preferred one. We still have a portfolio view of really trying to understand the merits and demerits across those different platforms. And then the final thing I wanted to share with you was our Spark program. And this is our way of reaching into industry and providing access to real life, cloud-based quantum compute resource. Some of the technical expertise to actually help people start to write code and examine real life problems within their industry sector, and bringing together like-minded people, forming networks and collaborations. And often some of the algorithms that crop up in healthcare or defense or in telecoms are shared, but those communities wouldn't normally connect with each other. And so we're trying to bring those emerging users together. And then finally, to ensure we're driving the growth in skills in this area. So whether that's through hackathons with early career research folks, or whether that's online courses, or again, we've been working with the University of Bristol to have more in-depth courses available as by way of continuous professional development. So hopefully it's given you an overview of the UK program. Very significant investment over 10 years. Significant investment will be ongoing into quantum technologies. And I think increasingly we're going to see a focus on how do we really drive societal benefit from quantum technologies, and looking forward to hearing more of your thoughts on how we can work ever closer with Japanese colleagues. Thanks very much.
Thank you, Michael. We are a little over, but I will allow a couple of questions if anyone has any questions for Michael or our guest speaker from Voice as well, Mr. Mizukami. Does anyone have any questions?